this is meaning is that the energy that existed in the beginning of time is still the same energy today. It just gets transferred and converted. So energy can change, but it doesn't ever go away, and it doesn't come from nothing. Now, there are tons of different types of energy. If you go to physics after this class, physics talks a lot about different types of energy. In chemistry, the main type of energy we're going to be referring to is chemical potential energy, which is the energy that exists from chemical reactions happening. Okay? Now, as we look at this, we need to recognize a few things with vocabulary here. That temperature changes indicate energy changes, but they are not one and the same. Temperature doesn't equal energy, but they are related to each other. Okay? We talked a little bit about energy in the last unit. Does anyone remember a unit of energy we introduced you to? Joules. So joules is the main unit of energy we'll be using, sometimes kilojoules. What's a unit of temperature? Kelvin, Celsius, Fahrenheit, right? So 2 different units. You can convert between them, but they're not like the exact same thing, okay? Now, the other big thing as we look at these reactions that you have to be aware of is recognizing, since energy cannot be created or destroyed, if one thing is losing that energy, something else is gaining it, and vice versa. So to kind of help us differentiate between them, this word system is what I use to say, what are we focused on? The system is what we're focused on. In our case, it's often a beaker or a test tube, right? The chemical reaction is the system. Everything outside of that is considered a surrounding. One big thing that is always a surrounding is a thermometer. The thermometer is not the system, it is a surrounding to the system. Okay, so kind of keep that in mind as we look at our examples. Okay? Oh, I forgot to erase my drawings from last period. Go away real quick. Delete. I forgot how to delete on my thing. Okay, there we go. All right, so let's first talk about endothermic reactions. Okay, if it helps you, vocabulary, if this is a new word for you, En, at the beginning of endothermic, you can think of as entering the system. So an endothermic process is where heat gets absorbed by the system. So heat goes into the system and it's being absorbed by it. Okay, in a sense that heat is going to be used to do work inside the system. So it's not just going in and being stored, but it's going in and being used up. Okay? Now, there's a lot of different ways we can look at it here. So in terms of a chemical reaction, the first way we're going to look at here is that the heat is flowing into the system, and so overall it has a positive delta H. Someone by raise a hand, can you remind us? We saw delta H last unit. Mary, do you remember where we saw it?
Change in heat.
Good, yeah, so delta is change, and then H, we'll learn more next time. It actually represents this thing called enthalpy, which is heat. It's just enthalpy is the scientific name for it. But delta H is the change in heat. Have a smiley face, Mary. So positive change in heat means heat is going into the system. That's why it's positive. Yeah?
Is that kind of like the sun's energy going into the ground or making it hot?
Yeah, so the process of the sun heating up the sidewalk, if the sidewalk is the system, right? And the heat is going into it. Yeah, that would work. That would work. Now, notice here that we have 2 types of reactions written. I want you to notice the difference and the similarity. So here's the first one. Once again, that positive delta H. Notice the difference between this reaction. They're both endothermic, but it's written different ways. Can someone by raise a hand identify for us, like, what's the difference there between these two? Yeah, go ahead, Matthew.
On the top one, it's just showing off to the side that it came underneath of kilojoules. And then on the other side, it's showing it as a reactant to show that, like, heat goes into the process.
Perfect. So once again, that's just 2 ways, both saying endothermic, okay? Have a smiley face, Matthew. So in the first one, it's kind of put outside of the reaction as like, hey, delta H equals this number. You can also include kilojoules in your reaction. If it's endothermic, it's going to be on the left side because it's like a reactant. In a sense, endothermic reactions need heat to move forward, at least that minimum amount of heat, okay? And then our last piece here is the connection with bonds, okay? So the breaking of a bond is considered an endothermic process because it takes energy, so energy has to be absorbed for that bond to be pulled apart. Okay, so keep in mind that bonds are not like firecrackers, in that when they break, energy doesn't come out. It actually takes energy, which if you think about it, what's happening, that should make sense, right? If I want this to come apart, energy has to go into it, right? I have to use energy for the bond to break, okay? So the breaking of a bond is always endothermic. And then our final bullet point here, my bullet points are black, so you can barely even see them on my slideshow, okay, is with a thermometer. If it's an endothermic process, the thermometer is going to measure a decrease or go down because it is part of the surroundings. And so the system is going to take heat from the thermometer, causing it to go down. Questions on endothermic? All right, let's flip to the opposite to go to exothermic. Okay, so exothermic, obviously everything is the opposite, but let's talk through it. So we have a negative delta H, right? So notice a negative kilojoules in heat indicates that it's exothermic. Now keep in mind, negative is just the direction that it's going. You can't actually have negative heat. Like that's not a tangible thing you can hold, right? But it's the change can be negative because of where it's going. I think of it very similar to a bank account. If my bank account is negative, is money going into my bank or out of my bank? It's coming out. So exothermic results in a negative because of the direction it's going. Okay? Notice in our reactions here, so same thing. In this reaction, we now have the kilojoules on the product side. Notice when it's in the reaction, we don't write it as negative because once again, it's not negative. Negative is just implying the change that's happening. Okay? And then oppositely, when a chemical bond is formed, energy gets released. So the formation of bonds releases energy, and we would measure that as an increase in temperature. Okay, any questions on that before we do our demo here? Okay, so when we look at a chemical reaction, okay, and once again relating it to bonds broken and bonds formed, often both things are occurring, okay? So what I'm going to do here, very simple, I'm going to get some water. Use my one I already had wet, okay? And then I'm going to mix it with some ammonium nitrate. Oh, your job is to identify whether this process is endo or exothermic and justify, okay? So claim evidence reasoning, is it endo or exothermic? So we saw ammonium nitrate when we did that, like that firework-like demo in the lab. You remember that one right before the break with the catalyst? I'm making a mess. Okay, so I'm gonna mix this with water. So before we even do that, let's think about what's happening with the bonds. Okay, so this is my ammonium nitrate, very toxic Dippin' Dots.
So don't.
Are there bonds breaking or bonds forming or both in the process of this mixing with water? What do we think?
No, it's not.
A tiny bit. It was when I put like just 2 drops in. So if this is going to dissolve, thumbs up, break bonds, thumb downs, form bonds. If this is dissolving, what's happening? Are the bonds breaking or are they forming if it's dissolving?
Neither.
It's just dissolving, then nothing's breaking.
Yeah. So I guess
Is it ionic?
It is ionic.
Oh.
Tell me this, if it isn't going to dissolve, if I poured them together, what would we see? Nothing, right? So if any type of dissolving happens, whether it's ionic or covalent, some type of force is being broken. Now we have our pretend bonds, which are intermolecular forces,
Oh, we're including.
but those also are going to take energy to break. Okay? So notice here in this first step, I just found this image, but I realized to me the colors feel backwards. This represents the water, and this represents our solid. Okay? In order for it to dissolve, once again, if you were to take it kind of piece by piece, well, the water molecules have to come apart from each other to make room for the solute to get between. And vice versa, the solute has to come apart from itself to break down. So in this first step, is that going to be endo or exothermic? If the bonds are breaking. Good. So label this first step here, everybody. Oh, that's not a pencil. So this first step is going to be endo with a positive delta H. But then the process of them coming together is forming new bonds, right? These relationships, even though they're just intermolecular, is still a new type of bond. So our last step is exo. So almost every chemical reaction is going to have endo and exo steps within it. How then do we know if the overall is endo or exo? Yeah, Stephen, what do you think?
Whichever step happened last.
Ooh,
The bigger one.
there it is. Yeah, so going back to our graphs that we learned from last unit, if the downhill is bigger than the uphill, then it's going to be exo. If the uphill is bigger than the downhill, then it's going to be endo. But keep in mind, both are pretty much always happening. It's pretty rare to have a reaction that is purely just the breaking of a bond or just the forming of a bond. Okay? All right, now to gather some data to help us make a claim, we're going to do it. I'll bring it around and you can touch the beaker and then decide for yourself if it's endo or exothermic. I ask that as you touch the beaker, to gather your data, you keep on your poker face so that those around you can experience it for themselves and you don't give away what you're claiming. Does that make sense? Okay, just simply to help me, well, I don't know. It didn't really work last period. Never mind. Ignore me. Okay, so I'm just going to pour it in. Mix it up.
How come you're using a metal thing instead of a plastic?
I just forgot to grab something else. And I had this handy. Okay, I'll bring it around. Just go ahead and give it a little touch on the side with your finger. And then, flip your page, your notes over to the next page, and there's a box to write down your claim. So in that first demo box, in that far column where it says explanation of connecting, that's just like your observations, which are pretty simple in this demo. Sorry, let me go to the next one here to clarify. So on this one here, so right here you'll write your observations of what you saw happen with your eyes. This is symbolically what's going on at the molecular level. And then this is where you should have your claim stating endo or exo with evidence and reasoning. Okay? Sorry, did you all touch it before I walked away? Oh, good poker faces. Once you have your evidence, go ahead and write down your claim in that box. It's very good. Atomic Habits. It's fun because you know why he named it. Chemistry. So like atoms are the smallest thing and if you you start with something small and then build it up over time, great things can happen. It explodes. Okay, did I miss anybody?
I always thought it was talking about like.
Not quite. I'm gonna let you guys.
That is very temperature.
Okay, write down your claim with your evidence and reasoning, then we're gonna have you share with your table here in a few seconds. It does eventually dissolve all the way and go clear. It just takes a little bit. Set your pencil down when you have your claim and evidence and reasoning. Okay, pink dot, you're gonna go first. Share what you wrote with your table and then go around to everybody else. Ready, set, go.
The reaction is endothermic. When an endothermic reaction has occurred, temperature drops due to the energy being stored.
Yeah. Mine is just endothermic. The beaker was colder. If it's colder, it's taking heat from the surrounding area.
Okay, I'm gonna pick on a few random people to share with the whole class here. I think we're all on the same page, but I think there's value in hearing different ways people say it, right? And especially if you're trying to improve like your FRQ answers a bit, right? The best way of making them concise, but as accurate as they need to be, right? That's what we want. It's nothing long, but also has what it needs to be. Okay, antimony, that's someone in my middle table. Mary, tell us what you wrote.
It said, after reacting, the resulting solution is cold to the touch. Energy was flowing into the system, taking heat away from its surroundings. Therefore, this reaction is endothermic, negative delta H.
Oh, just your last part was like not
I'll
negative.
take
There you go. Good catch. Good catch. Have a smiley face, Mary. That was perfect. I like, once again, it's a great way to know when you're describing something is like creating a visual for someone else to see, right? Makes it very clear. All right, let's hear from another person. Magnesium. Is that my table who's not here? No. Oh, go ahead, Marilyn. Perfect. Good. Have a smiley face. Very well said. Okay. Questions on understanding this from, once again, all three sides of our chemistry triangle, right? What do we see with our eyes? What can't we see that's going on at the molecular level? And then symbolically how it looks? Yeah.
I had a question on this graph or whatever.
Yeah.
Why did it end up exothermic?
This one?
Yeah.
So in this case, this was, once again, just an example. This wasn't matching like ours, right? Are you saying how do we know that it's exothermic? the only way to know would be to actually have to have the values of these things and to know that this step's delta H was greater than these delta H steps. Does that make sense?
Wait, so
Yeah.
Is that 1 step, 2 step, or is that it looks like 1 step, 2 step equals these products?
Oh, gotcha. Not really. No, it's kind of just like this is like the whole process of it dissolving. Like it doesn't really happen piece by piece, right? Like when I dump it in, it just all happens.
Yeah.
But if I'm imagining all the bonds breaking and all the bonds forming, this is kind of how you can look at it. So, does that make sense? I see what you're saying though, where this arrow kind of implies like this plus this, which it does in a sense, but in terms of the energy, it's a different way to look at it.
Yeah.
Yeah, Will.
So endothermic is like absorbing energy, meaning does it have more energy after the reaction is finished?
The system does, yes, but that energy is getting used, right? And so it's not like it's going to be hotter like after, right?
It won't be holding the energy.
It's not holding it. No, it's taking that energy to break the bonds. So, does that kind of make
And
sense?
exothermic is releasing energy that's stored in the bonds.
Yes, yep, exactly. Okay, now it's 50-50, so you kind of know what my next demo is going to be. I mean, I guess I could do 2 endothermic demos, but we'll do it nonetheless. So let's look at it symbolically first, and then we got to go into the lab for this one. So our reaction we're going to do, there's kind of 2 steps. The main reaction I want you to classify and justify is this second one here. Okay? Is I'm going to be reacting some glucose, sucrose, with oxygen. I just have to do something beforehand to generate that oxygen to make it happen. Okay?
Not enough oxygen in the air.
It's not concentrated enough to get it to go without it. Yeah, good question though. Yeah.
On the first one, if it just makes the surroundings cold, would it, like if you touch the liquid, would it be the same temperature or would it be cold?
So the tricky thing is your finger is always the surroundings, right? So even though I dip my finger in there, it's still gonna feel cold because it's gonna be pulling heat from my finger. Does that make sense? Same thing like with a thermometer. It would do the same thing.
But
So
if you like measured like the temperature of the molecules, it would be the same.
it's the key thing, a difference between temperature and energy. If you could, we don't have a way, but if there's a way to actually measure the energy directly inside the bonds, right, that energy would be going up. But because that energy kind of gets taken and then stored, right, we don't see it as temperature because it's like inside the bonds that were broken. Does that make sense? Yeah, good question. Okay, you can leave everything here. Just bring yourself and your eyeballs into the lab. Do I stop the video or just make them sit here in silence? I hate putting videos together.
You gotta like.
It's just yes, yeah. This one is definitely a big overlap. The difference is in general chemistry, this is as much as you did. In AP, we're now going to do the math side of it, of like calculating the energy. But okay, everybody ready? Okay, here's where you're going to show me to help me see your answers. I encourage you, even if your sign is different than everybody else's, to still show it to me, because that's how I know how to help you, right? Don't be embarrassed. Nobody remembers your mistakes like you do. Everyone's going to walk out of this room and not even remember if you got it wrong. But if you don't show me that you don't understand, then I don't know what to do. Okay? All right, if you think it's exothermic, you're going to make an X with your arms like this. If you think it's endothermic, you're going to make like this. It's just the opposite. Like my big stretches is like end zone. Endothermic. I didn't think that one. I just said NX. Not X. Okay, number 1, show me your sign. Number 1, what do we say? Show me your sign.
Wait, what?
Number 1, show me your sign. Number 1, have a smiley face if you said endothermic. Can someone, for a bonus, give us an explanation of how we know that? Leslie, go ahead.
Because it has, it's like plus the characters on the side.
Good. On the side, right? Keyword she said there, the delta H is written out of the equation. And its value is positive, which means energy went into the bank, which means endothermic. Good. Let's see, have a smiley face. Okay, number 2, show me your sign. Number 2, how did we classify it? If you're saying exothermic, have a smiley face, you're correct. Someone want to give us a Y to help us out? Go ahead. Yep.
Because energy was a product of the reaction.
Good, right? So now it's inside the equation, right? There's no delta H equals and, right? It's on the product side, which means it's being released. Good, have a smiley face. Questions on that one? Okay, show me your sign for number 3, everybody. Number 3 is endothermic. Good. Have a smiley face, everybody. And number 4. Awesome. Endothermic. Good. Have a smiley face. Well done, guys. Any questions on identifying endo versus exo? Yes, Mary?
On number 3,
Yeah.
does it mean the temperature of the water goes down or the temperature of everything else?
Whenever we're measuring the temperature of a reaction, the thermometer is going to be inside the system. Does that make sense? I mean, it's kind of the same either way. But like, so it would be like inside the beaker, but that doesn't make it the system.
Right.
It's still a surrounding to the system. Does that answer your question? I know, the thermometer component honestly is often the trickiest. Sometimes feels backwards because of like focusing on the wrong side. So yeah, Will, and then Mason.
So in the first equation, the change in heat, what exactly is that referring to?
So that's showing the overall change in heat from reactants to products was a positive 112. Does that help?
Yep.
Mason.
Does the beaker count as surroundings?
Yes. Yep, the beaker is a surrounding too. Any other questions? Yeah.
Just as like, you know, an objects lesson, can we get those tiny little balloons that you get like in elementary school where you smack them and then the reaction goes and you get a tiny little balloon?
I have no idea what you're talking about. Tiny balloon? Does anyone else know what she's talking about? You smack a balloon?
No, there's like what? It's like a thing. I'm pretty sure that like you hit the balloon and then it does like some reaction and it like inflates and it's like yay big. You get them for like Valentine's Day
I've
and
seen-
stuff.
It's like
No, no,
it's like a flat thing and you smack
But it gets really cold.
Yeah,
That's the point.
I know what you're talking about.
Okay,
A
so the
foil
point here-
balloon.
Yeah.
Okay.
The point here is it gets really cold, so it'd be a great
Oh.
endothermic.
So it creates a gas because obviously it gets inflates, but then it's an endothermic
Yeah,
reaction.
it's like really
Expand.
Okay, I'm gonna Google this on YouTube, not YouTube, Amazon, and see what I can find. Foil? I don't even know what I'll type.
Balloon smack.
Expand.
But they're like a Valentine theme?
Expanding balloons.
Yeah, like that's where I do.
Okay, I
Like
will.
happy birthday. You like open the thing, you hit the balloon. It's like get really cold. And, like,
I've never heard of this.
I don't know.
I will find it so we can all experience what Miriam is talking about. Yes, Will.
I did have one more question referring to the equations.
Yeah.
So, on the first one it says positive 112, right? If you're going to put that into the equation, so that's reactants to products.
Uh-huh.
So would that mean the 112 would be the products?
It would be, the idea is kind of like where the energy is getting, like, so when we put it in the reaction, it's really for the overall, but the idea is it represents where's it being, like, used. Is it being used to take it in or being put out? So, like, if this one was written in the reaction, we'd see 112 kilojoules plus arrow.
But wouldn't it be on the other side because it's gaining 112 from...
So that's the idea, is the thing of when we put it in the reaction, it's still gaining it. But the idea of putting it as a reactant is because of how the heat is being taken in.
So it's saying positive 112, it's gaining either way.
Yes, yes.
just depending on where it is.
Does that kind of make more sense?
So the ones above will always go in reactants unless it's already put into it.
Yes. But it's not like it just belongs, right? It's the overall still.
Like it goes into
Yes. Yes, making it happen. So. Okay, eyes up front here, everybody. Let's wrap this up. So 6.2 is really mostly a review on our energy diagrams we learned last unit. So these are our energy diagrams, right? This idea of the activation energy, right? We labeled these last unit. Really the only new part to add to today is just saying endo or exo. Last unit we just said energy released or energy absorbed. Now we have a specific vocabulary to classify to them, as well as bringing in the idea where every time you're going uphill, that's the endothermic steps. The downhill is the exothermic, and then the overall is determined by which one is more. Okay? Once again, forming bonds would be your uphill, breaking bonds would be your uphill, forming bonds would be your downhill. Yeah, Mary?
So, if what we were measuring was temperature,
Yeah.
would the graph be upside down?
Like this graph or like?
Like that graph? Like, would it be the same line but like upside down?
So temperature-wise, it's only ever going to climb, or it's either only going to just go up or just go down.
Really?
It's not, I guess once the reaction's done, then it'll eventually like level out. But as an exothermic is happening, the temperature will just keep going up because heat is just being pushed out. Versus endothermic, like on mine, I should have put a thermometer in there, but the temperature would just keep going down until it reaches the minimum it can go. Does that make sense?
Yeah.
Yeah, good question though. Marilyn.
Just a really quick, by the way. So on the homework, is it 6.1 and 6.3 or 6.2, 6.1, 6.3? Because it
So the homework is just about 6.1. So the paper is only about 6.1. The quizzes is 6.1, 6.2, and 6.3. So, but once again, you'll see 6.2 and 6.3 are very minimal compared to that. This is our only slide on 6.2. So, questions on energy diagrams? Okay, 6.3 is about understanding heat transfer, which actually relates to the second law of thermodynamics, which is that heat always flows spontaneously from hot to cold. Okay, so heat always flows from hot to cold no matter what. And if those two objects are inanimate, they will eventually become the same temperature. That's the idea of thermal equilibrium. So imagine here with me, I have a hot piece of metal, that's A, and I have a cold piece of metal, that's B. If I put those two metals together and let them sit, eventually they will become the same temperature. Because the kinetic energy of this one will start hitting that one, and they'll become the same. Okay, a very simple experiment, if you don't believe me, is you can take your hand right now and grab the leg of your chair. In first initial contact, for most people, it feels a little chilly. But if you leave it there long enough, eventually it doesn't feel cold anymore because your hand has equalized the temperature of it. So it kind of depends, on the, some people it doesn't feel as cold because if you have, bad circulation and cold hands. That's true. You aren't an inanimate object. But it will still, nonetheless, it will continue to suck heat out of your hand until it's safe. That's how you get hypothermia, is because heat just keeps leaving your body to try to reach equilibrium. And then to the outside of the world.
the outside.
So heat exhaustion, it's kind of the opposite. That heat from the outside is going into your body. Yeah, I never thought about the opposite, Gavin, but that would be true too. That heat exhaustion is because you've overheated your body. We're a little different, right? Because our body tries to fight against it versus a piece of metal, which will drastically adjust to whatever temperature. But homework tonight should be super quick. You honestly could probably finish 6.1 in 2 minutes. It's just 10 questions telling you if it's endo or exo. So it's pretty quick. And then just the pretty quick, the quizzes should be pretty quick too. So how do I stop?